Okay, I guess it's Dan. Go ahead.
Okay, can you explain again about how activation function can do non-linear work or linear work?
Okay. Is that part of the question, homework? I think.
Yeah, yes. Yeah, I was reading the book, but I'm not
Right.
understanding that.
Okay. Uh, right. Let's see. Let's see. So, the homework question is really about how neural network allows nonlinear, um, or how, what allows neural network to be able to handle nonlinear patterns. I think that's pretty much the question. And part of it may be the activation function. So, uh, I think the key to understand that is seeing the difference between logistic regression and linear regression. The key difference is really you can think of a linear regression also as some kind of neural network, but it only has the net input z. Z part is the same, even though we typically don't talk about it in regression context. But imagine a linear regression similar to neural network. In fact, you can have a linear activation, which becomes a regression essentially, and one single neuron. So the difference is only about the sigmoid activation. It can also be other activation functions, but sigmoid is one example that's classic. You can refer to it. What it does is, um, if you imagine the sigmoid function, where the x-axis is the y-axis is the activated value, and it's an S-shaped curve, right? As you increase z, the activated value tends to increase, but it increases at different marginal speed. Within -1, maybe -1 and +1 range of the z, it acts like a linear line, somewhat like a linear line, with a steep slope. So in those regions, active okay, right. In those regions, activation is quite sensitive. The activation function is quite sensitive. The Y response is quite responsive to the signal in Z. This allows a model to quickly adapt to changes in these small regions, and by maybe small changes to the Z net input, activation may go from 0 to 1, right? That makes sense. So these may be, you can think of it as that, you know, you can think of it as imitating a model of purchasing behavior of a customer. So what do you care when you go shopping? Maybe let's talk about electronics. What do you care most? Do you care brand more? Do you care coupon? Do you care price? Do you care warranty or things like that? These are a list of features or list of variables that will perhaps change your decision in terms of do you do you pull the plug? Do you buy it? If the discount is large enough, it it can nudge your uh, net input function slightly to the right, and if it's in the region of that -1 to +1, the region of z, your activated value could change from zero point 0.4 to zero point 0.6. And zero point 0.4 means, the model doesn't predict you will buy it because it's below 0.5. But if it changed to 0.6, then the model predicts that you will buy. So in small regions of Z, the model can change the sign and change prediction. And if you think of the model as imitating your decision-making process, that's how, small changes in the input can change the decision or change the outcome of the model or your decision making. But outside that region, large changes. If your purchase decision process goes like this, I will only buy this if the discount rate is as much as 20%. If it's below 20%, be it 10%, 8%, 2%, 1%, I don't look at it. I won't consider at all. And particularly when you see 5%, it's like garbage. I mean, it's like no discount at all to you. You won't even consider 5%. You probably will consider a little bit when it goes to 16%. It's close to your 20%, right? You will give it more thought. Maybe you think you won't even be able to wait until you get the 20% deal. So you probably will go for it. So at the 15 to 20% discount region, it could change your decision very significantly. It could change your decision. But in the region of 0 to 10% discount, you won't even give a thought. So, it's similar to how the activation function is not very sensitive to the net input when it's outside the narrow region in the center. So this is a long answer, I realize, but in short, activation function allows for nonlinear capability of the neural network by, I guess, by allowing the neural network to respond to signals differently at different regions of the input or the net input, different regions of the net input. In certain regions, it's very sensitive to the input. Small changes in an input can lead to change of decision. Outside those regions, even large changes to the input won't even change the result of the output. So I guess that's one answer. You can adapt. Does that make sense?
It kind of makes sense for me. Yeah, it
Okay.
is.
What about others? Can I get some feedback? Either I'm asking the other in the audience. Either it makes sense or it doesn't make sense. And if it doesn't make sense, which part doesn't make sense? Let me know.
I'm sorry, can I understand like activation function is like the control thing, like control the inputs into some range?
Oh, it's better to do this. So let me share my screen. Let me do some drawings here. 1 second. One second. Okay. Hold on. All right. Let me share my screen. This is the Zoom whiteboard. Okay, that works. Can you see it? A whiteboard?
Yes, I can.
Okay, so I'll draw a graph and color. Okay, right. So Okay, 0 to this minus 1 plus 1. You know, Z net input, right? The net input is, right, it's a similar concept in logistic regression. Net input is a linear combination from the input, and which is the first step of the forward prompt. Make sense?
Yeah, yes.
So this is the activation, activated value. For now, we're talking about sigmoid. Okay, and its value is bounded between 0 and 1. So if you use different, if you input different values of Z that goes from negative infinity to positive infinity, you will get something like this, an S shape, right? So in these regions, small changes of, around 0, small changes of Z is going to significantly change the output, and this is 0.05. If the input is 0, then the Sigmoid activation function is 0.5. If because of changes in the input data, you could the Z input value can go from minus 0.1 quickly to 0.1 to plus 0.1, and the activated value could go from 0.45 to 0.55, which will change the Y predicted value. Y predict value can go from 0 to 1. So in these regions, the output is very sensitive to the input values. Small changes in the input data could lead to big changes in Y predict. There are only two outcomes here. We're talking about binary target, right? So this acts like a linear function. It's quite, and the slope is quite steep for this, sort of linear function. But in these regions, in all of these regions, when Z input is smaller than -1 or larger than 1, large changes, even if you change from here to here, the input, the activated value changed this much. It changed much slower and less sensitive to big changes in Z. The difference between how the activated value respond to the changes in Z net input value, depending on the region of the net input value, is sort of a nice feature of Sigmoid activation function, and as well as a lot of other activation function that has similar shape. You have a 10H, which goes like this. It has a wider range, but the basic shape is similar. That means the advantage is basically similar between Sigmoid and other similar activation functions. So the difference between red and green is an advantage of nonlinear activation, which becomes the capability of neural network or logistic regression or neural network to tackle nonlinear patterns in the data set. Okay, tell me how you think.
Yeah, it makes sense. Thank you so much.
Okay, yeah. Great. And you can always rewind the video and to review these. Any other questions from anybody about this? Good? Everybody is good? So homework 3 is due next week, right? Not this week. Gives you a little more time. I guess next week, if you have questions, we can also talk about it. So I'm going to start today's content. It's going to be pretty fun for today because what? Because you will or I will demonstrate some TensorFlow. I think for many of you, it maybe is the long waited. You may have played with it, or you may have some issues or challenges, and anything related to that, as well as other models. If you are interested, ask a question. Ask a question now, or ask questions later. Ask questions when I demonstrate those. Anytime. No stress for today. And because the content of today is not going to be covered in the homework, it's not in the homework. I'm not saying it's not in the final exam, but I'm kidding. It's not in the final, but it could be related to the final project, right? If you want to train your model better and improve your model, you better listen today, because some of these that I talked about today is going to be very helpful for you to improve your project. That's obvious. Right? So, as I said, download those materials now, but please don't run these. Don't run the more demo, but you can run the basic demo. And I have all those run on my end. I'm going to show you the HTML version of both versions, and I will talk about the implementation of the improvements. So let's get started. I will switch between the slides and the demo during the lecture. Let me share my screen. All right, can you see my slides? Can anybody see my slides? Raise a hand or anything. Okay.
Yes.
Great, thank you. Make it large. Okay. All right. Now, I will talk about a few steps back. I think. Okay. Hold on, sorry. Somewhere. Oh. So this is the plan today. Based on the implementation from scratch, I'll talk about these improvements. 2 of these are already made into videos. I have yet to make these videos, but because the homework will not be related to these, I'm taking my time. But I'll talk about these today so that it covers back. If you ever have a question, you can let me know. Open source packages, 2 packages related. I'm only going to demo TensorFlow, Keras. I'm not going to demo scikit-learn. As for scikit-learn, it's not a bad package in terms of neural network, but it probably isn't one of the hottest thing you want to spend your time in. I'm not suggesting that you don't spend time. Go ahead and spend time, but if you want to prioritize, definitely spend more time on TensorFlow, and Keras provides more. It provides the potential to use more advanced deep learning networks. So that's a plan. Adding regularization to the prototype version of the neural network. As with the logistic regression, it's not a big change. I'm going to share my screen of the cheat sheet with you so that it becomes quite clear the scale of the change is minimal. So this is the cheat sheet I posted on Blackboard. The changes for the implementation, if you want to implement the L2 regularization, this is L2, are indicated in these blue circles or purple. And the change of code will depend on the kind of regularization that you implement. And just a quick refresh of memory here, regularization, what does it do? It adds a penalty to the model to prevent something that you do not want to happen as much in the process of the model learning. And typically for a lot of models, as well as including neural networks, we are talking about those pitfalls of machine learning model training that will lead to overfitting, right? We always have this overfitting problem because we do not have the entire possible, well, we don't have data for the entire population of the phenomenon that we're interested in. We always only have a sample. And because of the fact that it's a sample, some of the variances in the sample can be considered noise. You don't want the model to pick up those noises to the extent that it will not generalize well to the new data set. So that's the summary. And specifically, the type of regularization that we're talking about now is to add one more term or maybe a few more terms, typically one term, to the cost function to regularize the way that gradient descent is achieved. In a way, in human language, this means that the additional term will prevent the model from going into the extreme to somehow increase some of the coefficient just in order to jack up the accuracy or model performance level for the training set. You want to prevent that. So an effective change, if you compare the learned coefficients between a model that doesn't have regularization and another model that has regularization, is the size of the coefficients, some of the coefficients, right? A model that is not regularized, when it's overtrained, you will observe that some of the coefficients are much larger than expected. It can go to the region of 50 or 100. For a model that takes inputs that are scaled, that are properly scaled, you would never expect a good model to have a coefficient size of 100. I'm not talking about the number of coefficients. I'm talking about the size, the value of the trained coefficient. If you see a coefficient that of a model after training in the size of 100, you immediately know that this model has been overtrained. So L2 regularization, it does exactly that. It prevents the model from, going into a spiral of increasing the coefficients for some of the input variables just to increase the model performance. There are, of course, other types of regularization that we're not going to talk about. We don't have that time. One of the popular ones is dropout. You may have heard about it. Dropout can also even be used in a fully connected net if you have more than 4 or 5 layers. But for the kind of neural network that we're doing in this course, we will not benefit from dropout. You can learn about dropout by searching Google. There are a lot of materials online. You can read about those. You can find some videos in YouTube as well, the quality of which may not be good. But if you have more questions about dropout, simply let me know. I know some about that. I use that in training models in my research. Dropout is very good. It's very useful in training at least the convolutional neural network to deal with pictures, data set, image recognition, image classification. Those problems will benefit from dropout. And the logic of why dropout works is quite interesting. It actually, after knowing about dropout, it changed my viewpoint about how machine learning works. So it's kind of it's an elevation of the philosophy to some extent. So big applause for whoever invented dropout as a technique to prevent overfitting, as one of the weapons that you can use to regularize the model. There are other kinds of regularization in neural networks. You can specify the model to skip layers for some of the node by random. So, but that's kind of even more advanced than dropout. So we're not going to talk about those. But regularization serves a purpose. There's no point to go too far with regularization. Regularization can limit your model's performances as well, as good as it can provide a safeguard for overfitting. It can prevent your model from achieving lower bias. If you somehow accidentally put in too much of regularization, your model suffers from high bias. So that's one of the drawbacks. So there's no free lunch. It's not black and white. There are always some middle ground. Questions? All right, let me talk about the details here. If you have a pretty good understanding of the implementation for the basic version of MLP, the prototype model, including forward prop and back prop, which is much more complex than logistical regression, then the only changes that will be needed here is one change in the initialization process. You will need to initialize a parameter, which you will also set and remains unchanged throughout the learning process. So you will use this L2 prom, which is denoted lambda in the equations, but we can't use lambda as a name for variable name, so we have to use something else. Use L2 prom. It is the size of the regularization, or the weight of regularization. The larger this value, the more regularization you have that's effective on the model. In the extreme case, you can try, if you have L2 as large as 1,000, then your model will not improve at all. It's too much regularized. It's like have a law that are too restrictive. Nobody is allowed to go out of their house and buy food, then they starve. Things like that. So you have too strict of a policy, there's no well-being. So you want to choose regularization to an appropriate level. So that's one change. Inside the model training, there's no change in the forward prop. The first change happens to the gradient calculation. And it's only the weight matrix gradient that's affected here. We only regularize the weight matrix. We don't regularize the bias term here. So, and since we only have two hidden layers, the one hidden layer and one output layer, which is kind of also hidden. So we only have two steps here that will be affected by regularization. So these 4 bubbles, it doesn't mean four lines of code to be changed, only 2 lines. This is just the math term. So 2 places to change, 3 places including the initialization. Then 1 last place to change is the performance calculation. When you calculate the cost, since regularization essentially add an additional term to cost, you will need to add this term to the cost function. And the way it's implemented is exactly the same. Well, not really. It's not exactly the same with logistic regression. Because we have 2 weight matrices, we are adding 2 terms. In logistic regression, we only have the single neuron. We are adding 1 term over there. Here we add 2 terms. So there's the 2 terms. And for each term, it's a grand sum of all the elements of the weight matrix after being squared. So in the math term, you can kind of see that it's adding all the columns as well as adding all the rows. In the case of logistic regression, it's the weight vector is only a vector. So we only add the 1 vector together. So it's slightly more complicated here, but not as much. Python code remains very straightforward. NumPy the sum, without specifying the axis, it will take the grand sum of all the rows and all the columns, essentially all the elements of the matrix. And adding 2 terms together is all the L2 regularization term to be added to the cost function. Any questions here? I think it's quite straightforward. Look at the implementation here. So L2 L2 implementation in initialization stage. The only change, or the only effective change, real change, is adding the L2 prompt. I also reduced the epoch from 1,000 to 400 because in the regularized model, you perhaps don't need that many training, because as long as the model stabilizes, it achieves a balance between overfitting and regularization. The model stabilizes. More trainings don't change the model effectively. You can see the curve, and it's quite clear. As versus for a model that's not regularized, if you keep training, it could become more and more overfitted to the model. The model will keep improving.
Excuse me, Professor Ma?
Yeah?
I have a question. Is there a specific number of epoch that we should begin with?
Oh, epoch?
Yes.
Yeah. So if you recall, when you were learning the Adeline and logistic regression, we only did like 50 epochs, and that was enough. Any more epochs made the model more overfitting. And with the regularization, 50 epochs was kind of enough. Here, the data set is larger. The problem is more complex in the sense that it's less. The outcomes are less separable. You know, it kind of requires a bigger model to be trained. So with that said, here we need more epochs. 50 probably isn't enough. We need probably 100 at least. And once after 100, you see that the line stabilizes. So guideline for epoch depends on if the problem is complex if the data set is large, if the problem is challenging enough to the in the sense that if the outcomes are easily separable. For binary target variable, less epochs is needed. But if you have a target variable that has 10 categories, you would definitely need more epochs. But still, a general guideline in terms of epoch. Epoch is part of this concept of training time, right? Epoch is the amount of training, typically. Amount of training, sometimes people refer to it as the number of minutes or number of hours, but really it's a number of iterations. So, and you probably hear other people saying early stopping. That might be one of the questions, right? What's early stopping? And do you do it? Is it useful? I don't recommend early stopping, because essentially what early stopping means to stop training the model before the model becomes too overfitting, right? I think the only okay, let's see. The only motivation for reducing the training time or reducing the number of epochs is to prevent it from overfitting. I think that's the motivation for the question. Is that Melanie?
Yes. So is it okay if we use, for example, for Adeline model, instead of 15 epoch, we use, let's say, 100 and test it?
And you mean test it?
Yeah. So
Yeah.
in
A
case
lot of
of
testing is
overfitting.
needed when you are dealing with a new data set, especially particularly. But so maybe early stopping is not really related to your question. But again, so here is the guideline. For a new data set, a new problem, you never know what the optimal epochs is. So experimentation is needed. That's the first thing. You go from what your experience tells you, and because you have been cleaning the data and you have done some exploratory analysis, you have a reasonable idea of how complex the problem is and how large the data set is. So you have a reasonable guess. You may start from 50, or if you think the data set is, if the data set is the most complex data set you have dealt with, then go with 100 first. And observe the progress, right? How long does it take for one epoch to finish? If it's a split of a second, then you have nothing to lose, even if you train for 200 epochs, right? So those are small changes. But once you have experimented with a few different values, and really, when do you stop? You want to make sure that the model is sufficiently trained. But where do you stop? Do you stop early, try to avoid overfitting, or another way to ask a question is, do you risk anything if you train it a little bit more, right? If 100 is perhaps enough to train the model to the level of a good performance level, do you lose anything, or do you risk anything if you train it for 200 epochs? Will the model get worse if you overtrain it? With a good understanding of overfitting and regularization and how to use them, how to apply them to the models, you would almost never have a concern of overtraining. With good regularization, even if you train for 100,000 epochs, the model remains stable. So there's no concern about the upper limit. If you read about early stopping, I would suggest that you skip that. Early stopping is not a problem once you have a good understanding of regularization. So, does that answer the question?
Yes.
Professor?
Yeah.
I agree that I agree, but sir, with more complex problem, and too many approaches, I think it's going to take a lot of time.
That's right. That's right.
Because of full batch gradient descent, it's going to take a lot of time.
Oh yeah. And even with stochastic gradient descent, because it's one more for loop, and you'll see it today. It takes longer time.
Yeah.
Yes, time. If time is a factor, then yes, you don't want it. You don't want to waste too much of time. So that's another element to optimize about. But again, regardless of that, the same mindset will apply. There's no concern about overtraining in terms of model performance. So you want to make sure you train the model sufficiently. You don't need to be over careful about trying to stop the model early in order to avoid overfitting. That's not a concern. But if time is another precious resource, then you want to time it just about the time when the model is for sure sufficiently trained, and then you can stop. Right. Any other? Great. So that's epoches. Then in implementation, 3 places are being changed. They are indicated here on the side. One change happens to the weight matrix gradient function of the output layer. One change happens in the weight matrix gradient function for the hidden layer. It's backprop. We go from outer output layer to hidden layer. A third change happens to the cost function. You have a third line here. The line is becoming too long, so I have to cut the lines. This is the end of line or line continuation symbol. You cannot have anything after this. Otherwise, Python will complain. This means the end of line, but line should continue from the next line. So that when Python is compiling the code, it will read 3 lines here as 1 line and process it. So here, the added 2 terms are the L2 norm of the 2 matrices. Training for 400 epoches with regularization only took 2 seconds here on my laptop, which is pretty good. And when you plot the learning curve, the cost curve, and the accuracy curve, the same oscillation happens for the accuracy, for the reasons that that was mentioned last time, mostly because of the whole training set gradient descent. And with small changes to the gradient, it can overshoot the target and oscillate around the best optimal solution. And this problem, this slight issue is going to be resolved shortly after we implement the mini batch gradient descent. But here it's only 4,000 epoches. The line is continuing to improve. But so here is one difference between a model that doesn't have regularization and a model that does have regularization. And let's compare these. So I'm going to make a screenshot here. I'm going to take this screenshot. So this is the curve of a model without regularization. You see 1,000 epoches. And here is a model that has regularization. So up to 400, that's where the boundary is for the model with regularization. Another difference is that I updated the cost to be the average cost. So you see the scale is quite different. But the curve shape shouldn't change at all. So if you compare these two, the most dramatic difference is that you see that in the model without regularization, the curve changes faster. I think the model is able to learn or do the optimization process without any constraint, right? Regularization is putting a constraint on the learning process. So without any constraint, the learning process happens faster. You see the curve is steeper, or it improves faster. With regularization, it improves slightly slower, and the curve is less steep. So that's the only difference here, not much else. With the model without, without regularization, the accuracy on the training set exceeds 90% around 300 epochs. But for regularization, at 300 epochs, you have this dip, and after the dip, the performance is not yet close to, but not yet 0.9. So, and you see that the line is continuing to improve at 400 epochs. So again, it slows down the optimization process because of regularization. But as I said, with a sufficiently trained model, the model will stabilize at the optimal level. So no concern over there. You don't want to stop early. That's what I'm saying, right? You don't want to stop too early, at least. So that's the implementation with L2. Any questions? Test set accuracy is 0.92. Sufficiently trained. The best possible level may be 0.93. So with this amount of training, this model is hitting the best possible almost. And there's no overfitting here. So next I'm going to talk about mini batch. It's a slightly more involving process. And in the video, it's also explained what the difference is in terms of the implementation flow. The change is mostly because of an added for loop inside the main for loop. So there are two for loops. Because of that, the training time slows down. But optimization efficiency was increased. So let me highlight the differences. I'll just go to the very end, skip these animations. So on the left-hand side, you have the whole training set gradient descent. The essential steps are within each for loop, after initialization, you have a forward prop and a complete backward prop, and save the performance, calculate the cost, calculate the accuracy, and you're done. That's the simple process. But when you have mini batch gradient descent, you have additional steps. Before you start the main for loop, you need to generate an index to refer to the rows of the training set. Mini batch gradient descent is essentially taking random subsamples from the entire training set, and for every iteration, it's using a different set of random samples. But if you add them all together, it's the entire training set. So, but you also want the randomized order of the random set to be different across the iterations, because the benefits from mini batch gradients or stochastic gradient descent is the stochastic part. You want the model to not be able to anticipate what's coming. from the data, so that the model is best improved. If the model knows what's coming next, the model will be too much tailored to the data set to sacrifice efficiency. So, but you cannot really sort the training set. It's not a good idea to sort and resort the training set. So what you can do is, let's say you have a training set, right? This is the training set. With the whole training set gradient descent, you simply input this, and we do the net input. You do the net input is the calculating z is x time matrix. What is the term for the weight of the hidden plus the bias for the hidden. Okay. So you throw in the entire data set. That's what we do. We don't do any anything additional to the training set. But with mini-batch gradient descent, we have to randomly take subset, and let's see, use these as a batch 1, and then don't sample it again in the same main for loop. In batch 2, we will sample these sort of, it's hard to draw, but randomly take these. So one way to do that is you restore the training set and simply take portions in order. And when you go to the next main for loop, you resort the training set, or you randomize the training set and take portions in order. In practice, we don't typically change the order of training set, because in that case, you mess up with the original training set. It's not a good idea to do that. But what you can do is to leverage the leverage the index of the NumPy array. If you have a NumPy array, it's two-dimensional, it's a matrix, and you can slice rows by using some kind of index, right? And in that case, you don't even need this. By specifying the 0 axis, you can take rows according to the index values. So you only need to construct index values, and which is sort of like a 1D array. You have this index, and you randomly shuffle this index instead of shuffle the content of the training set. And the outcome is the same, but the effect is different. You didn't mess up with the training set. You only shuffle the index. So that's a better practice. Once you have this indexer, within each of the main for loop, you will shuffle this index. Once it's shuffled, you guarantee a different mini batch process. After it's shuffled, in the first mini batch, you take the first X number of rows, and the second batch you go down the list until you have used all of them, and that finishes the inner loop for this mini batch iteration. You go to the next iteration, which is the EE porch. You shuffle this again, and the program will make sure you don't get exact shuffle throughout the process. It will take a very long time before you will exhaust all the possibilities and begin to see duplications. It's almost never going to happen with realistic training that we use. So that's the process. The the process is clear, but when you look at the code, it's much more involving. The initialization process has one thing new here. You have a mini batch size, and we typically go with, let's see, the size of the mini batch. We typically go with 2 to the power of n. N can be 2, 3, 4, 5, 6. You'll go up to maybe 8. And why is that? I don't know. Maybe because of a convention. But if the power is 2, you get 4. So mini batch size is 4. Every time it takes 4 rows from the training set and finish that mini batch and go to the next batch. With power of 3, you get 8, and so on and so forth. So the largest I've seen, if you have 7, is 128. The largest is 256. I've rarely seen anything larger than 256, but you may be surprised. I don't know. I haven't been surprised yet. And with most cases, 256 is enough. Even with very large supersized data set, which use online training, they rarely go beyond 256. So, and you don't have to remember all these numbers. You simply use Python code 2 to the power of n, and you choose the n. So, right, so it's easy. Okay, so let's look at the code. Everything else remains the same in the initialization, but when you go to the implementation part, you see a lot of the new processes here because of the added index. And for the index to shuffle, you need an additional random number generator. Within each of the for loop, the first thing you do is shuffle the index. You have this index, you shuffle the index, and then you go to each of the mini batch training. Inside the inner loop, you go through each of the mini batch. And so in this case, you need to specify the training set, X and Y. Here is Y. Wait, here Y is somewhere here. Here's Y when you calculate the error. You update the X and Y data by only using the batch index for the current mini batch. So that's the most things that are different. After the inner loop finished, you only have finished one loop of the outer loop, which is one epoch. So here you exit the inner loop and go to the outer loop. You will calculate the performance, and you do the forward proc, calculate the cost, and calculate the accuracy, and you finish the epoch. So with two loops instead of one loop. Training time, remember training time previously it was 2 seconds. Now it took 14 seconds, 7 times as much time to train for 400 epoches. So that's the difference. As much as it looks like a downside instead of a strength, you know, why do you even need it if it's slower? The reason is whole training set gradient descent is a luxury in real life or large data set, big data project. With a big data with maybe 10 million rows, you try whole training data set gradient descent, you put your computer to death. So if that's not possible, I guess you can only go with mini batch. So that's the reason. For smaller data sets, perhaps whole training set gradient descent is maybe better. But again, with the TensorFlow, you don't even have that option anymore. With TensorFlow and Keras, you have to implement mini-batch gradient descent, even though it seems to be counterproductive for smaller data set. That's just the way, I mean, that's the priority of TensorFlow, because those who really benefit from TensorFlow are using large data sets or more complex, or dealing with more complex problems. So whole training data gradient descent is not realistic. I guess that's all for mini batch gradient descent. Any questions? Nope. Great. Cost curve, I'll skip that. For here, I'll only say that the cost curve here, I mean, validation curve, the validation process here is not the cross-validation. It's different. Cross-validation is a process where you can implement the validation process across the entire data set. But here, this validation process is a convenient process. You reserve partial training set for the validation process. It's not a systematic cross-validation, so keep in mind. Of course, you should use cross-validation, k-fold cross-validation, more than this convenient validation process. But here it's just a convenient way to evaluate the learning process. Earlier we were only able to look at the curve. Oh, by the way, if you run the mini batch gradient descent, when you look at the curve, the oscillation went away. So this is one of the plus sides of mini batch gradient descent. Even though it takes longer time, it get rid of the oscillation, which is quite obvious earlier. If you compare these two, the advantage is obvious. You don't have this great drop in performance anymore. The model is much more stable and reliable. So that's definitely one of the plus sides. And so I was saying, for validation process, now here is a convenient solution. I won't talk about the details. I want to get to the TensorFlow much more quickly. So here, what we did is we reserve a small part of the training set and labeled it as validation set. When we train a model, even with mini batch, we do not include that small validation set in the training process. And the validation set is only used after the mini batch is finished within each of the outer loop. So we go to the outer loop. This is inside the outer loop. We do the mini batch only with the train. So only with the train. This is training set of the training set. So now we have a validation set of the training set. This train is the higher level train, and this training is the lower level training. We also have the validation set. So that's the difference. We only use the training of the training set to train the model, finish the mini batch gradient descent. When we exit the inner loop, we will calculate the model performances for both the train and the validation. So here is the difference. Training set, conduct forward prop, calculate cost, and for the validation set, do the same, but this time with the validation set, not the training set. So that's the difference. Same thing in calculating cost, in calculating the accuracy. So what's the advantage here? The advantage is that earlier we were only able to see the curve for the training set. There's no way we can see overfitting from these charts because there's only the training set. And you know that even with regularization, if the strength of regularization is not enough, you could still have overfitting. Based on these charts, the chart alone on the training set, you cannot see any signal about or feedback about overfitting. With the validation curve, you can. So I'll talk about this a little bit later. But so here is the benefits. If you have both train and validation, this is a validation set. This is accuracy. So if the two lines are quite consistent with each other at both levels when the model is sufficiently trained, you almost guarantee yourself that there's no signal, there's no feedback about overfitting. The model is good. There's no high variance. This is to show any variance between the training and validation set for the model along the model training process, right? Now, so here, if you wonder, so this is the average cost, both graphs. This is the average cost for the real training set, the training set of the training set. This is the average cost of the validation set of the training set, the small portion of the training set we reserve for validation purpose. With the cost is continuously improving for the training set. The cost improving initially, but it gets much worse. And it gets worse and worse after 50 epochs. Why is that? And if you think you have the answer, then think about this more. Even if the average cost has deteriorated almost in the entire process, the performance of the validation set didn't get worse at all. And why is that? Is it overfitting? If it's overfitting, accuracy should get worse. Why does the cost get worse, but the accuracy didn't change? Think about it. And this is quite interesting, actually. So what are your thoughts? Anybody? Or ask questions, you know, that may help you get closer to, you know, knowing what's happening here.
Can you repeat the question, please?
So you see four graphs here. The two graphs on the top are showing the cost value, average cost value during the training process. The two graphs on the bottom are the accuracy curve, and these are accuracy value during the training process. The two graphs on the left are based on the training set, the real training set that the model is trained on. The two graphs on the right are using are the results based on the validation set in the training set that the model did not use to train. It only It's only used for evaluation after each epoch. So we have another trace compared to previous versions. We have another traces of how the model performed on a validation set during the training process. The question is, why does a cost curve for the validation set look so bizarre? And it's showing it gets worse after only 50 epochs, and significantly worse, I think. But somehow the accuracy performance was not affected.
Does it have something to do with the K, the K?
I think the model was overfitted.
Yeah. So I mean, if it's overfitting, why does the accuracy not change? It's a good point, though. So why? Think about wildly.
Yeah, maybe CrossFit. I mean, cross-validating. Did we get the validation set correct?
You mean the code may have a problem?
Not the code, professor. I think maybe the values in a validation set, the y values.
Oh, the values are wrong. Not very. I mean, very unlikely, I should say, because it's a random sample from the data set and it's randomized. So what else can you think of? Let me check. Yeah. I'm looking at the codes again just to make sure they are right. Cost is in validation. Yeah. Validation. Yeah, should be right. So, do you need more time or reveal the answer? Now, let me give you a hint. This has something to do with the activation function, which is the topic I'm going to talk about next.
Is there something to do with the hyperparameter tuning?
Not really. I mean, that will affect the overall performance level, but not likely affect the differences between the train and validation set. I mean, the model essentially is the same across the same epoch point of the two lines, right? And this is quite clear on the accuracy graph. So hyperparameter is not, I mean, it affected how the model performed, but it shouldn't affect the difference between train and validation set.
Because when I was reading the text, it said something about the model that works with the test set. You can optimize it before it even sees the full data set, before it even gets trained by the data set, you know? it had something to do with the k-fold, the k thing, k-fold cross
Oh yeah,
validation.
we don't have k-fold here. So
Okay.
k-fold is not implemented here. K-fold cross-validation affecting, it's kind of a separate topic.
Okay, thank you.
But here it's not used. But yeah, good thinking. I mean, you need to go outside of your think outside the box kind of thing, because it's very puzzling at first. Why is this happening? If you observe the curves of the accuracy, you do see a deterioration, right? If you compare these two, and if you put one line over the other, I guess you can make that graph, but I didn't make it for the sake of seeing it side by side. But if you plot another curve using different color here, you'll kind of you'll observe that the cost, I mean the accuracy for the validation curve is somewhat deteriorated over the region of 150 and 250. 150 here is quite concave curve, but here it's kind of a linear. So it goes like this. It has a smaller slope here. And by the time it's trying to 250 epochs, the model gets back to track 250. But for the training set, for the real training set, the model is already sufficient at around 170, 80 epochs. So the validation set performance took another 80 epochs to get back on track. And this is mostly because of the impact here. The impact is the largest when the curve turns before it bends down, before it slows down. Here it slows down the performance curve for the validation set. So you can kind of get a hint, but still, why is it happening? That is the question. So let me tell you this. So the difference is here. And more specifically, the reason you can say that it's because of this. So let me talk about this before I talk about the hidden layer. Here is quite straightforward, even though it's quite straightforward, even though the function here is quite bizarre. Output layer, in the previous implementation, we used Sigmoid. So with the Sigmoid, here is what happens here. So Sigmoid is for every node in the output layer. Sigmoid, this is what it does. It activates the Z to the activated value by using this function. Its range is between 0 and 1. If we use Sigmoid activation on each and every, I mean, not this one, this is input, but on each and every node in the hidden and the output layer, particularly on the output layer, this is what happens. If we have Sigmoid here, we go from Z to activated value. Let's say for one example, you have an activated value of 0.9. So this is predicting, in the case of default, credit card default, this is predicting no default. So this output node is predicting label of y equals 0. And the second output unit is predicting label of y equal 1. That makes sense, remember, right? So if the activated value for this particular output unit is 0.09, then the likelihood of this customer not defaulting with a label of 0 is 90%. Pretty good. So pretty much no default, right? The likelihood of no default is 0.9, 90%. So if I ask you, in this case, what should be the predicted likelihood for default? Ideally, it should be 1 minus the likelihood of default, of no default, which is 0.1, right?
Yeah.
Now, you wish for, if you have sigmoid on both of these nodes, this would not necessarily happen. What happens here is, based on the training here, the model will make two independent predictions for these two likelihoods. So this is not likely to be 0 or 1, even though it could. It's likely to be 0, 3, 0.3 or something. So you see an inconsistency. If you add the predicted likelihood of the two outcomes, it's greater than 1. In the sense of likelihood, in the sense of probability, it doesn't make sense, right? But this is the disadvantage of using sigmoid on all of the output units. So,
Professor,
yeah, go ahead.
but isn't this the reason we choose threshold value?
Yeah.
I mean, isn't this the reason we have a certain threshold value? In most of the cases, 0.51. Then we decide if the customer defaulted or not defaulted.
Yes, you could adjust your. I mean, so you can do anything with the model. I mean, the model won't tell you it's wrong or not. So in a sense, you can adjust your threshold value. But I would strongly advise against that. You would never, I mean, in other cases where you have unbalanced data or unbalanced, unbalanced outcome, where the cases of 1 versus 0 is strongly unbalanced. Maybe 5% of the data has label 1 and 95% of the data has label 0. This is a case of an unbalanced outcome. In that case, what people do, I would say amateur analysts, what they do is, as a workaround to this unbalanced data problem, is to adjust the threshold. That's a no-no. That's a no-no. You sacrifice two things. You sacrifice the integrity of the model, and you sacrifice your out-of-sample prediction. So I strongly discourage that. What you want to do is to resample to deal with that problem. But here, you could adjust the threshold for these, or maybe even 2, try to hit the balance where it equals 0, equals 1. But I would say you'll have a very hard time to balance these, right? I mean, which way do you go? I mean, do you set threshold of 0.4 and 0.6? Or, I mean, how do you set? Do you have any guidelines to help you? Perhaps not, right? So if you found materials that can help you answer this question rigorously, then that's good. As far as I know, this is discouraged, and this is, I mean, certainly this is one way, but that's not the best way. Make sense?
Yes, sir.
Yeah. So but yeah, go ahead.
Yeah, so it's better to get the probabilities rather than values?
I mean, it's better to use the appropriate activation function. That's it.
Correct.
But here I want to talk about this because this explains why you have that curve.
Yes.
If you, yeah, let me go back to the Jupyter. So what happens here is that after some time, the optimization process somehow leads these to move in a way that, or maybe including the two, because these two are still independent, sort of, right? Their values do not really depend on each other. They depend on the betas, all the betas, as well as the bias, all the weight matrices and the biases of the net. Once these are fixed, the activation is fixed for both of these nodes. But somehow the optimization still changes these based on the cost. And what happens is that somehow, because of there's still some level of unbalanced outcomes here. There are, I guess, maybe 22% with 22% one case and 78% zero case. And because of the unbalanced data set, this is going to have an effect on the cost value, because the cost is an average. If you have unbalanced proportions of these cases, if the model will see this, the model sees that if I improve the cost of this group, I'm going to achieve a better performance overall. So the model will de-emphasize this portion. That makes sense, right? And these two proportions of the data correspond to these two output units. So somehow the model finds it's more rewarding to optimize this one. It's less rewarding to optimize this one because of the unbalanced composition and because of the way the cost value is calculated. It's just an average. It didn't have different weights to upplay this node, right? So out of a unbalance, the optimization process will somehow learn to optimize this one over this one. But if that happens, then somehow, the cost value, because of this prediction gets, or the cost value gets worse and worse, and somehow it affected the overall cost. So, you see the shift, the model, but the model corrects itself and eventually goes back. In this case, if you keep training for a long time, it could still go back because model realized that, the overall cost is not improving, it's getting worse. So it could go back. But small changes of these, let's say in the optimal model, in the absolute optimal model, this prediction should be 0.99. This prediction should be 0.01. The result is clear. But in a less optimal model, even if the prediction is not as optimal, this becomes 0.7, much worse. And here, this becomes 0.6, even worse, because both of them is greater than 0.5. But that doesn't make a difference in terms of accuracy. This node is going to rule still, as long as it's larger than that one, right? That's how argmax is taken, is making the impact here. Argmax will basically compare the activated value of these two, regardless of if they are larger than 0.5 or what, the threshold. Here, we don't even involve the threshold. We compare the value and choose the one that's larger. It's as simple as that. So as long as the model gets this right, the accuracy won't be affected too much, but the cost curve is affected. I hope that makes sense. So very intriguing phenomenon here and very interesting. It tells a lot about, several things: unbalanced outcomes, optimization process, how the model can learn reward versus punishment, and the evolution of the model, and how cost deterioration won't affect accuracy too much. But I guess this perhaps is because of, another reason is because of the data set that we are dealing with. It's a fairly simple data set that will allow you to kind of isolate these factors and to see the impact. In much more complex data set, perhaps you don't even observe this, but some other problem or bigger challenges is going to be in a way. So that's the validation curve. Any questions? Right. So I was talking about a better activation function, right? Now, a better activation function is a softmax. So what is it? Essentially, other than the functional form, essentially what it does is, let's assume the output layer only has 3 units. What it does is it will make sure activation 1, 2, 3. The softmax will make the softmax will make sure A1 plus A2 plus A3 is 1. So it guarantees a combined likelihood of 1, so that each of these activation can be interpreted as the predicted likelihood of that particular label, the confidence for that prediction label. That makes sense. If this is object or image classification, the first label is cat, the second label is dog. What's the third one? Be creative. Turtle. Okay. So that's going to be an easy problem for the computers. But if A1 is very large, 0.9, A2 and A3 is going to share the rest of the likelihood. So maybe like this. So softmax makes sure that the activated value of all the output units will add up to 1. That's what it does. And how does it do that? Instead of applying sigmoid, what it does, you can look at the functional form. It's a fairly large equation. I'm not going to write it, but what it does is it will get the z, right? It will get the net input of these 3 output neurons. It will do a transformation first. It will take the e to the power of z. This is 2. What's the effect of taking the e? It makes sure the value is greater than or equal to 0. E to anything is greater than 0, not even equal. So all of these are positive. And after that, it calculates the activated value as such. E of Z1 over E of Z1 plus E of Z2 plus E of Z3. The denominator is always the same. It's the sum of all the activated values of all the units. The only thing that changes is the numerator, the corresponding e to the power value. So that's how, if you add these all up, it's always going to be 1 mechanically. So that's how it does it. You can observe the math function, and this is one example showing the math function. So it's all the improvements for, oh, by the way, I haven't said these. Rectified linear unit, ReLU. Perhaps have heard about it. ReLU is quite interesting. ReLU is a preferred activation function for the hidden layer, for all the hidden layer, even for CNN models, for all the hidden layers, because it's easier to optimize. The ReLU function is like this. It's a conditional function. If z is greater than 0, it returns z as the activated value. So in a sense, in this portion, it's linear activation. Both portions are linear, but if you add them together, they are not linear. If the value of z is smaller than 0, it's always going to return 0. So the value is lower bounded by 0, and there's no upper bound. As versus sigmoid activation, there's upper bound of 1 and lower bound of 0. So quite different. You know, somehow this looks like a worse version of that, because this, at least this part is smooth almost entirely, but there's a kink over here. And even linear activation, we said that add-a-line model is not as good as logistic regression because of its linear activation. How come the linear activation here is making the model better? It's too complicated. I don't know how to say it. But anyway, it's not as complicated. I can say it, but we don't have much time here. So what it does is, I mean, the gain here is, the benefits is it makes the gradient function much easier, because here the gradient function is much less easy to compute. Here the gradient function is just 1 in this region, and 0 in this region. So gradient is easier, makes it easier to find the global optimal point for the gradient descent, and improves the model convergence. We can see that effect here. So with both implementation, changing the Sigmoid activation to ReLU in the hidden layer, and changing the Sigmoid activation to Softmax activation in the output layer, this is what happens. You know, review the changes to the code. They are minimal. This is what happens. You do not see that problem anymore. You do not see that deteriorating average cost on the validation set anymore. The change, you know, the only thing that changed from the previous implementation to here is the activation function. And I don't think that ReLU made an impact. It's mostly the Softmax that made an impact. So I think Softmax solved that problem. And another difference is what does ReLU do? ReLU helps increase the efficiency of optimization. So you can observe the speed of model improvement. And when does the model improve to being sufficient? At around 50 epochs. The model on both the train and validation set improved to be sufficient, and there's perhaps no more room to improve. Training set approached 91% accuracy around 50 epochs. Same thing, and maybe even earlier for the validation set. Validation set performance approaching 92%. This is 92.5%. So not as high as that, but close to 92%. So at epoch 50, the model is almost ready. But if you take a look at previous implementation without the alternative activation function, the model took 200 epochs to become sufficiently good. So that's the difference of choosing an appropriate activation function. So from this time on, when you implement neural network, using either TensorFlow, Keras, or scikit-learn, make sure that you always choose ReLU for the hidden layers. Any questions? Now we can talk about the TensorFlow. Any questions for everything before this point? I guess if there's no questions, we also don't have much time here. I'm trying to finish by 8, so I only have 7 minutes. But by the way, I like to. I hope you learn a lot from this course. You know, I designed the course in a way that you have a lot of takeaways and you have a deeper understanding of how the model. I mean, these models are not a black box anymore. They are an open box for you, and you found a lot of treasures from these models. That's what I hope. So I'm going to send a informal course evaluation form. That's informal. It's not official. I'm going to send it to you, or I may post it on Blackboard. I think it's a Word document. Simply color or circle or make them bold. Make your choices and send it back to me. I will appreciate your feedback for me to understand how you think about this course. Because we're halfway through the course. Okay, so open source libraries. Sounds good? Anybody? Are you asleep? Yeah, I know you're not, but I guess you have nothing to say. Anyway, so open source project is quite fun. The Jupyter notebook is quite long. It's very long because it has the training. And let me show you what the Jupyter notebook will be after you have training those. So you have this long cell. What is it? It's training a model, a Keras model, a TensorFlow model, which is, by the way, that has 200 epochs. I decided to print one step in a row. So it's going to, you will have 400 rows, because including that table, the header. So it's going to be long. But the Jupyter notebook, you can shrink it, right? So it doesn't have to be that long. If you print it as HTML, it's long. So there are 4 models here. The reason for those models are that I would like to implement the models using TensorFlow and Keras in a way that map to the 4 models that I talked about previously here today, right? So the 4 models are I guess 5 models. Or maybe 4 models. It began from the basic model and add regularization, and it added a better gradient descent, and it added a validation set, the convenient validation process, and then in the end, the last model added the alternative activation functions. So I like to map the 4 models with how they are implemented in TensorFlow so that you can see the relation there. What needs to be changed on the high level when you use a package, and what needs to be changed inside the implementation process using Python code from scratch. So that was my purpose. I will just highlight and spend time offline as you wish to study these codes. So again, these won't appear in the homework. These won't appear in the final. These may be or should be very helpful, I think, to your final project and your future data science exploration. So, you know, this is sort of an long-term learning process. And in building the models, and you can look at the slides and see how, you know, the process differs when you use packages. The process of training a model using Keras package is you define the model, you define the layer, you add layers one by one. It's quite easy to add a layer. It's much easier to the implementation from scratch, much easier, just one line of code to add a layer. Then after you have defined the model, you compile the model by specifying the optimizer, which is the sort of the gradient descent algorithm. You define a cost function, which cost function form to use. You have a bunch of selections. Use the documentation page down here to get more information. It's a website that it's a TensorFlow website that has so much information. And a model compilation process also has asks you to choose the model performance by default. I think it's accuracy for classification problems. And next, you will train the model by specifying the train data, X and Y. You can provide the mini batch size. Otherwise, it's stochastic gradient descent. You can specify the number of epochs or let the model choose for you. Then you go ahead and observe what happens. So the model will print out the epochs results as it trains. So, you know, this is what happens. It will add lines one after each other. It will show you which epoch it is. It will show the size of the training set. It will show you the average loss value and accuracy value after each epoch. You can see that with the very basic version with stochastic gradient descent, without regularization, without other things, it's the same functional form. The hidden layer has 7 units, output layer has 2 units, and the same input data set. It flattered, the cost and accuracy flattered for a long time, up until the 100, close to 90, wait, hold on, 93 or 100 epochs before it starts to improve again. So it was kind of trapped in a local minima of the cost function, I think, before it was able to escape that local minima and improve the model again. If you look at the cost, the learning curve is quite clear. You know, for a long time, the cost improved slightly, but the accuracy didn't improve. It plateaued until beginning 95 epochs. The cost further improved. That's when, you know, the effect has taken place in the accuracy, and accuracy improved dramatically until it plateaued again. It's going to remain at 89% for quite a long time again before it starts to further improve. One benefit of the Keras package is that after you train, what if, you know, we often have this problem. We decide on the epochs, maybe 50, maybe 100, and we train the model. After training the model, we found that it's not sufficient. We want to add a few more. We want to use, you know, if it was 50, we want to use 100. If it was 100, we want to use 150. What happens? You have to retrain the model from all over again with the implementation from scratch, right? You could write some code to save the model parameter and use an adapted version of the implementation from scratch and to start training the model using the saved coefficient. But you're going to spend a lot more time to customize the code to make it capable of accepting some, better initial values of the weight matrices. With Keras, you use the same model object. You simply fit again after training 200 times. You fit again, train 10 more. You say train 10 more, however more you want to train. It will use the model that was trained previously and keep and build on the training. So it saves all the coefficients for you. So that's a nice thing about that. So anytime you want to add a few more epochs, you can do that. And why does this benefit? Why is this important? The reason it's important is you see that when we train the model using our own implementation, you see that even when the model is stable, sometimes it drops significantly, but the model is able to quickly get back on track, right? So these are maybe 1 out of 20th epochs, or 1 out of close to 20, or 1 out of 30 epochs that this happens. But what if you are unlucky? You chose a number, 50 epochs. It happens to be a bad epoch. What can you do? You retrain again with the implementation from scratch. That's what you have to do. With these, you simply train 2 or 3 more epochs. The model gets back, and you can use that model to make predictions. So that's the added benefits of using this package. That makes sense? So I will very briefly talk about after implementing several things, after improved the optimization from using stochastic gradient descent to using Adam. Adam is a more complex optimization algorithm. It combines several features in it. There's one thing called an RMS prop, which is quite complex. I don't even know what's going on there, but some scientists come up with a better algorithm that is proven to be overall better. But keep in mind, overall better doesn't mean always better, and you'll see that. So change from stochastic gradient descent to Adam is the second second improvement here. And then I added validation. Model was very not good for a while. The third model used a validation process. With that change, in the results you see 2 versions of the loss and accuracy now with the training and the validation. So you can kind of observe whether or not there is overfitting in the process. So with that, you also get 2 more graphs. And finally, the last one is a major improvement. It's the activation function. It's the same activation change that we used in the hidden layer. I changed to ReLU. The output layer, I changed to Softmax. And after all of these, I put them all together and trained the 4 models. And these 2, not this one, the one setup number 2 of comparing the 4 models is going to take a long time because it's 200 epochs for 4 models. And it's going to take a good 20 minutes for your computer to finish this cell. But after that, let's see. In the first comparison, I ran 20 epochs for each model to see how the initial training compare across the 4 different configuration. Then I graph the training learning curve of the cost function as well as the accuracy. But the cost function is much more clear. Here it plateaus a lot. So the cost curve, I have fixed the y scale to be the same. So the height of the line in each of the graph indicates where the cost is. The higher, the larger the cost. You can see that clearly the last implementation with the better activation, as well as with the Atom optimizer, is the best learning process for the first 15, 20 epochs. In the first 20 epochs, this model is able to achieve almost the best result. Only 20 epochs. Look at the performance using the basic stochastic gradient descent. It plateaued after 5 epochs and it stayed there for a long time. Same thing with the one with regularization as well as Atom. Even with Atom, but with Sigmoid activation, the model seemed to not be able to escape the local minima very easily. And same thing when you adding the validations process. This one doesn't change the model essentially. It simply changes the size of the training set. The training set is smaller. That leads to the learning process becomes slightly smaller because the smaller training set. You lost information, slightly from there. So this is the initial process. The winner is the better activation functions, as well as the Atom improved. So it seems like the benefits of Atom is not realized in here and here until you have better activation function. When you have these two together, it's much better. Then I trained the 4 models for 200 epochs to look at the long-term improvement. And now it's clear that, again, the one with better activation improved very quickly. Up to 20 epochs, the model is sufficient. So you only need to train 20 epochs. That's the benefits of using simpler but more efficient activation functions. That's very clear. As compared to another model that eventually achieved the same or even better level of costs, it takes much longer time. This is 200 epochs. So close to 150, the model is as good as the one with ReLU. But it takes much longer time. And you say the cost value is even smaller. That's because of slightly overfitting, I guess, in these regions, because this model doesn't have regularization. It can go as low as it wants if you keep training it because of overfitting. If you look at the accuracy curve, without better activation, the better optimization doesn't help, and it's even worse in terms of being trapped in the local minima. The basic version escaped the local minima at somewhere around 100 epochs and managed to improve the model continuously after that. With better activation, you don't have that local minima problem because the gradient, the cost, the gradient function optimization is much easier to manage for the process. So that's the end. Out of sample performance using the test set, comparing the 4 models, the best model is actually the very basic version, believe it or not. Second best is the one with better activation functions. The 2 without better activation function and uses the more complex optimization is even worse. So lesson learned that even though some of the algorithm is more complex and fancier, it doesn't mean it will work all the time. In this case, fancier optimizer works even worse. It makes the gradient descent process too complex. The curve is too complex to navigate in order to find the global minima of the cost, which leads to the model being trapped. And another lesson is ReLU is better than Sigmoid, period, in hidden layers. And Softmax is better than Sigmoid. That's a no-brainer question. Softmax is better to be used as the output layer activation for classification problems. So that's all I need to. I have to say. I'll open it up for questions. I'll stop sharing, and I hope you enjoyed today's fun lesson without any pressure. And have a good night. Feel free to leave, but then I will open up for questions.
Professor?
Yeah?
Is it TensorFlow making use of your GPU course or CPU course?
It was using my CPU. My laptop doesn't have GPU.
Oh.
But you can definitely, I mean, by default installation, it's the same. Even if, I mean, regardless of if you have GPU or CPU, the installation will install the whole package. But if you have GPU, you may have to configure that GPU with that package additionally before the package can use the GPU. Yeah, but with CPU, you can still use the multi-thread, right? Multi-core.
I've been thinking about this, Professor. Just like we have better activation functions, better regularization and optimization process. Do we have a better cost function than binary cost entropy?
Better cost? Oh, yeah. I mean, for binary classification, it's binary cost across entropy. But for multi-label classification, it's the multi-class. So in terms of cost, I don't think there's the sense of better. There's a sense of appropriate, as long as you use the appropriate. That's
better in the sense, the way it can calculate more accurately.
Yeah. Any other questions? I guess not. So wish you a good night. Good luck with the homework. Let me know if you have any questions.
I have one more question, Professor.
Okay, go ahead.
So we've been talking about using Softmax because of the unbalanced composition of the output. So I was thinking, sir, isn't it the most common case in any data set? Because the target variable is going to have unbalanced composition, right? It's never going to be 50-50. Isn't it true?
Yeah. But in all the cases, you don't have that. That's basically it. And it has very good implication is that you have to deal with this issue. It's an unbalanced data issue. You cannot simply ignore it or pretend it's not there. You could resample your training set to make it balanced, but your model will be used to a balanced data set. But when you implement the model in the field, you're going to get unbalanced data, right? So you cannot go around that. So better tailor the training to unbalanced data set and do something about it than skipping the problem altogether. Yeah, unbalanced data is one of the biggest problem in real life. I mean, business machine learning.
Yes,
it's a hard problem. anything else? So this is all we will stop here in terms of neural networks. Next time, we may use some of the neural network to analyze specific model evaluation problems, but we won't go any deeper than this.
Got it.
Yeah.
And it feels much easier to use Keras because code looks single line or just double line.
Much easier, but you get these unstable results sometimes.
Right, sir.
Yeah, and it's hard to diagnose because it doesn't open up for diagnosis. It's like Mac versus Windows.
Exactly, I've been
If
thinking
you
the
want
same.
easy, use Mac, but
yeah,
good luck in digging out whatever is.
correct. Yeah, I was just coming there because it's really tough to diagnose where we're going.
Yeah.